à tous. Donc aujourd'hui vous êtes avec nous dans
American Interview.
Donc nous allons vous présenter Zach Rengert. C'est le nom d'un chimiste et biochimiste américain né à Indian Rocks Beach en Floride, qui a obtenu son baccalauréat en biochimie et en chimie environnementale de la Florida State University en mai 2012. Il a synthétisé avec un groupe de chercheurs qu'il a rejoint en juin 2012, le Basin Research Group, la première molécule d'oxydoréduction conjuguée à injection membranaire.
Cependant, les bactéries électrogènes jouent un énorme rôle dans le traitement des eaux usées, ce qui représente notre projet de TPE. Maintenant, vous vous demanderez pourquoi parlons-nous de Zach Rengert alors que tout un groupe de physiciens, chimistes et biochimistes ont participé dans cette recherche.
Zach Rengert nous a beaucoup aidé dans la réalisation de notre TPE. Malgré sa rare disponibilité et sa situation géographique, il a pu nous fournir de nombreuses informations concernant l'expérience du traitement des eaux usées que nous avons effectuée. Il a même accepté de faire une interview avec nous. Nous présentons tous nos remerciements à Mr Zach Rengert.
I'm Yasmin Misewi.
My name is Noor.
And I'm Fierce Rice. Nice to meet you.
Nice to meet
Nice to
you.
meet all of you.
Thank you.
Thank you.
Yeah, my name's Zach.
Yes, we know.
So,
So, as we told you, our project is about your new experience created in 2017, which is the creation of the first synthetic molecule DSFO+, right?
Right.
Yes. So we thought we could ask you some questions about your project.
Okay, sure.
so how did you and your group have the idea of creating the molecule?
So basically that started from looking at the proteins that naturally occur in
Yes.
these bacteria.
Yeah?
So these bacteria have these proteins that will span the membrane,
Yes.
Yes.
and in those proteins they contain an iron group.
Yes.
And this iron heme group is kind of similar to hemoglobin, which is in our blood, which is how oxygen gets transported through our body.
Yeah.
And so these organisms evolve to live like at the bottom of a lake.
Yes?
And so at the bottom of the lake, there's no oxygen. So there's nothing for them to breathe on. And so
Yeah.
they've learned to basically breathe on iron minerals. And so this is kind of like the opposite of rust. Rust is when iron 2 plus becomes iron 3 plus. So
Yeah.
these bacteria have learned to take iron 3 plus and reduce it to 2 plus. And in this way, you can think of electrons as being waste.
Yes.
So the bacteria needs to get rid of these extra electrons in order to eat food and
In
live.
order to use them and eat food and live, yes. We understand.
Right. So
And-
then we kind of drew inspiration from these proteins and tried to make a molecule that was very small and simple.
Yeah?
Because, proteins are usually really complicated and they're also hard to make synthetically.
Yes?
And so my project was about designing a molecule that could be made very easily and cheaply that could also somewhat mimic the function of these proteins. And so the term we like to use is like protein prosthetic. Because like if you think of someone who has like a prosthetic arm, or it's not as good as having a real arm, and two, it's not made out of the same materials as a real arm, right?
But it can replace
So
it.
this protein. Oh, go ahead. Sorry.
But it can replace it. Replace what
Yes,
the protein does. Yes.
Yeah, exactly. So like this molecule isn't a protein, so it's not made of a protein, but it mimics the function of a protein.
Okay.
And also it doesn't work as good as the real protein does.
Yes. So for the second question, why and for what purpose did you create this molecule? Like.
So, yeah, okay, yeah, definitely. So the bacteria I was speaking about that naturally have these proteins, they're actually quite rare.
The
so there's not many bacteria.
Schwanella, no?
Yeah, Schwanella is one, and there's
Schwanella,
another one called Geobacter.
Okay.
And there's a few other small ones, but the problem is we don't understand them very well right now.
Yeah.
And not many of them. And so the goal of this project was to make a molecule that we could give to any bacteria, ones that we understood very well, and
Yes.
give this property to them. So when I was talking earlier to Yasmin, I was talking about E. coli. E. coli is like the cheapest bacteria we have.
Yes.
it's very easy to work with. We understand its genome very well. We understand the molecular nature of a lot of the functions that go on.
And we can
And so
find
when we
it
add a
everywhere.
molecule like this to E. coli, we can study it very easily.
Yes, I see.
And also, it'd be very cheap from a practical standpoint.
Yeah, but it won't have the same result. It will be less productive, no?
Correct.
Then we
Correct.
will know.
And
But in the future, it could be possible to improve, right? So this is the first generation, the first go at it. So maybe if we can make some improvements on the design, we can have a molecule that'll function better.
I
Yes,
see.
I understand. Okay.
For the third question, how can this molecule reinforce an electrogenic bacteria's electricity production? Sorry, sir.
Yeah?
Did you hear us?
Okay, I'm back. I can see you now.
So you didn't hear the question?
We repeat.
I didn't. Sorry, please
Okay.
repeat.
Thank you.
So how can this molecule reinforce an electrogenic bacteria's electricity production?
Okay, so that's a good question. The short answer is we don't know. But what we think it's like,
Yes.
the analogy we think right now is that we've added more lanes on a highway. So, before there's only so many lanes that these electrons can go down the highway and pass from the inside of the cell to the outside
Now
of the
you
cell.
want to reduce
And
it.
now,
Yeah.
we add this molecule, and now there's, for example, one more lane for if the electrons are cars. There's one more lane on the highway.
I see.
But we really don't know. So we don't know if the electrons are participating with the proteins that are already there, or if they're completely going around.
Yeah.
And this is something that we're trying. Like I left the group because I graduated, but my coworkers are trying to answer now.
Okay.
Oh, okay.
So the question
But we
is
think
still,
that they can interact with each other. So there's no reason to believe that they're exclusive from one another, or that it can only go through one pathway. We think it could be quite complex, and that these pathways will just basically go to the lowest energy site. So what's easiest, most readily available.
So you are still thinking about it?
you are still doing research.
Yes. About
Yeah.
Okay, yes.
Yeah, we're doing actually a lot more. So trying to design molecules that have more complexity and have more similarities to the proteins that we were studying already.
Okay, I see.
Okay, how did the experience went at the first time? If it worked, of course, and if it didn't work, how many experiences did you make until it to succeed?
You succeed.
Well, okay, so making the molecule took me like a year and a half, and that was a lot of failure.
Yes.
Like hundreds of failures, maybe 300 failures.
300.
And then working with the bacteria, actually it worked quite well from the very beginning. But my coworker who was working, so you guys are making these fuel cells with the bacteria. You may notice that they're kind of
That's the experience we're doing.
yeah, they're finicky. Like, so one day it works and one day it doesn't, and you don't really know why. And this is bacteria. Like, I don't know. Like, sometimes bacteria will be your friend, and sometimes it won't.
So
but
it's just hazard.
Yeah.
If it
Yeah,
works
so,
or
like,
not.
a
We
lot
don't
of
know if it is going to work.
sorry.
We don't know if
Like-
it's going to work.
Yeah, I mean, so the guy who I was working with, he had a lot of experience. So once I gave him the molecule, he was able to make it work actually quite quickly.
I see.
But then we had to do a lot of work proving that it was working the way we thought it was. And this is a lot of electrochemistry. And so, yeah, we had about a year and a half, maybe 2 years of trying to actually show that what we saw. So we know that this molecule is improving the performance, but we didn't know how, And so answering how took almost 2 years.
2 years. I see.
Okay, and what makes it better than the other ways of water treatment?
If
It
it
does.
does.
So water treatment now, most of what we do is aerobic. So actually, one of the main costs of treating water is pumping oxygen into the water so the bacteria can respire.
Yes.
So if we can just basically close the lid and put an electrode in there, one, we don't have to pay to pump the oxygen into the water,
Yep.
and two, we can make some, electricity at the same time.
So it will be
And so the amount of
cheaper.
electricity we'll produce will just make, it won't be a lot, but it'll be enough to make water almost free to treat. You know, if you, like the amount of energy we make will be about equal to the amount of energy we consume.
So
So it'll be about
it will be
Cheaper.
cheaper and it will produce electricity, but not a big
Yeah.
amount of electricity,
Yes.
but it's
No.
it's what we need to treat water.
Yeah, exactly.
No.
So, do you have a new project in your mind that you want to develop?
So what I really want to do is make molecules that are more complex. So the proteins I was talking about, they have like about 10 to 20 iron centers in them,
How many?
and they're located close to each other.
How many? Sorry, I didn't hear you.
About 10 to 20.
Ten
Can you hear me?
20. Yeah, yeah.
Okay. And so the one I made had just one. So I want to make ones that have like 3, 5, you know, and start getting more and more in there. And the reason why is to decrease the distance between iron centers. So an electron doesn't have to go so far to hop between different iron centers.
And if
Yeah.
it won't have to go so far, will it be more, how can I say, productive, or will it be more, I don't know, if it doesn't have a long way to travel, what will that change?
It'll change the energy required for the electron to hop. So it'll basically make it faster.
Okay.
Thank you very much. Thank you for
Yeah.
your helpfulness.
Yeah,
And
no problem. I'm
thank
glad
you
that you're
very,
interested in the project.
thank you. And thank you very much for accepting the interview.
Yeah, no problem.
We are so grateful for all the help you gave us, and it was really an honor to talk to you.
Yeah, thank you. Yeah, I'm so glad you guys were interested. And if you have any more questions, let me know. I'm happy to help any way I
Thank
can.
you. Thank you very much.
We hope we meet you when we go to America,
Yes.
because we want
Yeah,
to go
let me know.
study there. Okay.
Great.
Thank
Goodbye.
Alright, have a
Thank
good
you
one.
very much.